Okay, folks, this is mass versus weight. They are related to each other, but they are not the same thing. So please take notes and let's get started. So, what is weight? It is the force of attraction between an object and the earth. So when we start drawing force diagrams, every single object will have the force of weight because all of our examples are going to be on Earth. So you draw that by drawing a vector that is an arrow pointing in the direction that the force is pushing or pulling you. So that weight vector is always pointing down, and we can label that the force of the weight. And there is a formula for it. It's not a reactive force. The force of the weight, which I sometimes call W, but this is better, force of the weight, is the object's mass in kilograms times g, which is 9.8 meters per second squared. Okay, it is what's called a vector, which means the negative sign is indicating the direction, which is down. It's really towards the center of the earth, but it appears to us to be down. So the direction is always towards the center of the earth, and the magnitude is the amount of newtons of the vector, or how strong the force is. All right. English unit of weight is pounds. The SI unit of weight is newtons, and 1 newton is a little bit shy of, or a lot, depending on how many digits you care about. It's a little bit shy of a quarter pound, so here is a quarter pounder. If you imagine that meat is a little bit less because you cooked off some fat, that's a newton. So it's a tiny unit. I mean, relatively small if you're talking about like massing people or cars or whatever. Okay, so that's weight. It's force of attraction. So what the heck is mass? And I chose this picture because mass is basically stuff, right? So the dog pulled the stuffing out of the teddy bear. That is representing the mass that used to be inside the teddy bear. The units of mass are kilograms. For a reference, a gram is about a paperclip. Okay, so might say, will you go mass something? And the scale might read in pounds, it might read in newtons, it might read in grams. Remember, you never feel your own weight. I hope we did this demo, or we'll do this demo in class. You're really measuring the stress on that scale. So this scale can convert that stress to other units, but it's really measuring stress, which is a force, but you can work backwards and using the W equals mg formula and solve that for mass, right? So there might be calculations going on inside the scale, but mass is in kilograms. All right, I found this interesting. Which of these objects, a cherry, a liter of water, pretend on an empty soda bottle, an apple, or a car tire is 1 kilogram? Okay, it is the liter of water. If you want to think about what 1 kilogram is, so think about a liter of water, that is a kilogram. Although, are these 2-liter bottles? A car tire is apparently 10 kilograms, for those of you who've changed a tire. Okay, so weight, in some ways, a little bit more basic. It's a force. You can imagine what a force is. Mass is really more abstract. What does mass measure? In addition to how many electrons, protons, neutrons, how much stuff you have, a more philosophical thing that mass measures is an object's resistance to a change in velocity. So one example is if you've ever seen a massive ship trying to turn around, stop, or start, that's going to take a really, really, really long time to go from 0 to 30 miles an hour, or from 30 miles an hour down to 0. Or trains, right? Massive, massive objects were going to take longer to get going. This is called inertia. Okay, please write that down. So mass measures inertia. So massive objects are harder to get going. And massive objects are harder to slow down. That is why the semis, you'll see the runaway tracks on hilly, like Pennsylvania roads, so that if they have too much, if they're having trouble slowing down, they can like drive into that spot. Okay, this is why I had you deliberately add 500 grams to cart B at some point in the collision lab, so that you could see that it was, that caused it to gain speed more slowly. Okay, why is it so easy to confuse these two concepts? Because they are related to each other. They're directly proportional. The mass is in the formula for weight. And unfortunately, in the real world, we use these words interchangeably when we shouldn't. You know, you go to the doctor and say, how much do I weigh? Or you say, I'm going to go weigh something in the chem lab, and you come back and say how many kilograms it is. Okay, so an astronaut on the moon has the same mass that they did on Earth, but a different weight, because the amount of stuff, you know, neglecting what they had for dinner, etc., the amount of stuff is the same. But since the moon has less mass, it's pulling on the astronaut with less force. All right, almost done. Now we're just going to do a quick calculation. We want to find the weight of a 68 kilogram astronaut on Earth, where you have one value for G, and then on the moon, where you have a different value for G. So we're going to use the formula for weight. So you do the calculations on your own and type in the numbers you get, and we'll check our work in a second. All right, I hope you got that right. On Earth, astronaut has a weight of 666.4 newtons. Again, divide that by 4, and that gives you a rough sense of their pounds. So they're about 167 pounds, very, very roughly. I rounded to a quarter. On the moon is only pulling them towards the moon with a force of 108.8. That is why it is easier for the astronauts to jump on the moon. All right. Hopefully this all makes sense, or you've seen it before. Mass versus weight. Oh, one more quick thing. You can see that there are hidden units, right? It's a kilogram meter per second squared. We don't want to keep writing that, so we're just going to replace that with a Newton. All right. Thank you for listening, and I will see you in class.